double and half angle formulas. So in our last video, we talked about the sum and difference formulas. So we were looking at being able to find things like the sine function output when you have a sum of two angles, alpha and beta, or maybe the cosine output when you have a difference of two angles. So as long as we know some of the like sine and cosine outputs of alpha specifically and beta specifically, then you can add those two angles together and find a sine or cosine output of that. And same thing with the difference of those. So that's what we looked at in our last video. What we're going to do is we're going to use that sum of angles formula to try and set up something like, how do we find sine of twice an angle, alpha or beta or theta or whatever we want to call it. So maybe we know the angle 17 degrees, for instance, and we know everything about it. We know all the sine and cosine outputs, and then from there we know all the other trig function outputs because they can all be written in terms of sines and cosines. If we know all that information about this 17 degree angle, then we'd like to be able to get that information about the angle 34 degrees, double 17 degrees. And you can kind of imagine how that's going to go. It's really going to be just using this sum of angles. So we'll do that. Then what we're going to do is we're going to build these power-reducing half-angle formulas. So technically the power-reducing formulas are different than half-angle formulas, but not actually. I'll show you that they're really just the same thing. They're just kind of written in different ways. And then we'll just use those. We're going to use those formulas to kind of get some practice doing some examples and things like that. So this shouldn't be too long. We don't have a lot to go over in this one. So how do we get double angle formulas from sums of angles? Well, I say if we want to do something like this, or if we know how to do that, then why don't we change that to sine of theta plus theta. If we just make both of those angles the same thing, this is sine of 2 theta. Easy enough. So what we're going to do is we're going to grab the sum of angles formulas, and we're just going to put the same angle in for both and see what happens. This is really not that hard. So alpha and beta are both going to be theta. So now alpha plus beta is 2 theta. So we need to go ahead and just fill in the blanks. So maybe I'll just let you pause the video. Go look up the sum of angles formulas here and put theta in for both angles and see what you get. It shouldn't be too much work. Pause the video and give that a shot. All right, hopefully you did it. So we can take a look at this now. This is what we've got. I've gone ahead and put both of the angles theta in. And so we have sine theta, cosine theta, plus cosine theta, sine theta. These are really the same thing. The order doesn't matter when we multiply this. So sine theta, cosine theta, and cosine theta, sine theta are really exactly the same. Just like 7 times 2 is equal to 2 times 7. The order of this doesn't matter. We can switch the order of those trig functions. So really both of those terms are the same thing. So we really just have 2 copies of the same thing. So 2 sine theta, cosine theta. That is sine 2 theta. That's our double angle formula for the sine function. If you've done that, go ahead and do it for the cosine function if you haven't already. You can probably see about how easy it's going to be now because you're just going to take the cosine sum of angles and plug stuff in. But I'll let you pause the video and go do that. All right, hopefully you've done it. This is what it looks like. Cosine of theta plus theta is going to be cosine theta minus sine theta. Well, that's really just cosine squared minus sine squared. So there we go. Notice this looks like a Pythagorean identity, kind of, but the sign is wrong. It would need to be plus in here for this to be the Pythagorean identity, but it's not. So we don't have the Pythagorean identity. This is not equal to 1, but there is something about the Pythagorean identity that we can use here. We can do some stuff with this. So the Pythagorean identity says sine squared theta. Ooh, let me fix that theta. That's a pretty bad one. There we go. Plus cosine squared theta equals 1. And notice we have some of those terms in here. We can shuffle those things around, and we can say things like sine squared theta is equal to 1 minus cosine squared theta. And similarly, cosine squared theta is equal to 1 minus sine squared theta. And so we can substitute these in. If we want, we could write this cosine 2 theta identity all in terms of cosine functions. We could swap out this sine squared for 1 minus cosine squared theta. And similarly, we could do this all in terms of the sine function. We could take this cosine squared theta and swap it out for 1 minus sine squared theta. So that's what we'll do here. There's going to be tons of different versions of this. So here's our double angle identity that we've got. We can swap out those terms. So here they are. I just went ahead and put both of them up. Let's just walk through them real quick. So I switched out my cosine squared theta for 1 minus sine squared theta. And then again, I'm subtracting another sine squared theta. So pretty clearly, 1 minus 2 sine squared theta. Then I've got this cosine squared theta minus sine squared theta, so I substitute 1 minus cosine squared theta in. The negative is going to apply to both, meaning this is going to be cosine squared theta minus 1, but then we're going to say plus another cosine squared theta. So that's how we have this 2 cosine squared theta here, minus 1. So for the cosine function, we actually end up with 3 different identities that are all the same thing. We can say cosine of 2 theta is this difference between the squares of those functions, or we can say it's 1 minus 2 of the sine squared function, or it's 2 of the cosine squared function minus 1. I know it's a little confusing, but once you got this first one, you can use the Pythagorean identity to just get all the other ones. So hopefully you've written those down somewhere. If not, you can always just pause the video or go back or flip through in the notes that I've got up on Canvas and see. But let's give this one a shot. Let's try this thing out over here. What we're going to do is we're going to say if sine of theta is 3 over 7 and theta is not in quadrant 1, so we'll figure out what quadrant is it actually in, then we want to find the values for 2 sine squared theta sine of 2 theta and cosine of 2 theta. So maybe what we'll notice is if I go back, let me grab this. Oops. If I go back here, let's just look at this one. If we want to find sine of 2 theta, notice we need sine theta. We have that. We also need cosine theta. So let's go ahead and find that. So first, sine theta is positive. Remember, on the unit circle, the sine is the y value. And so we're in a positive y value. That means we're either in the first or the second quadrant here, because those are the ones where y is positive. So since we're not in quadrant 1, we have to be in quadrant 2. So why is that important? Well, that means that cosine, the x value, is going to be negative. So we'll take a look at figuring out what our missing coordinate is. We need the x coordinate out of this thing. We have a y coordinate. Maybe I'll draw this using straight lines instead. We have a y coordinate. That's 3. We have a missing x coordinate that we need to find. And we have this nice radius here. So this is 7. This is 3. Here's theta right here. Well, really, theta is actually this angle. So maybe I'll get rid of this one. There we go. And now we need the negative x value. I'll give you a second to figure this out. We're just going to use some Pythagorean theorem stuff. We'll be able to figure out what's going on. You should be able to find this value pretty easily. All right, so hopefully you found that this side length is root 40. Or if you want, you could say that is 2 root 10. And it's negative. So for our own reference, cosine then is going to be the adjacent leg, negative 2 root 10 over the hypotenuse, 7. Okay, so why does this matter? Well, because we've got some formulas for sine of 2 theta and for cosine of 2 theta. So let's go grab the one for sine of 2 theta. Maybe I'll do this in a different color. I'll do this in blue. Sine of 2 theta is, we'll flip back up, and here it is, 2 sine theta cosine theta. 2 sine theta cosine theta. We have both those values. Bang, there's sine theta. Bang, there's cosine theta. So this is 2 times 3 over 7 times negative 2 root 10 over 7. So we've got 2 times 3 is 6 times negative 2 is negative 12 root 10 over 49. Whatever that value is, you could approximate it if you want. But I'm looking for an exact value anyway, so this is good. For the cosine one then, we'll say cosine of 2 theta. And here we've got options, right? If we go back, you could say it's the difference between those two things squared, or it's 1 minus 2 sine squared theta, or it's 2 cosine squared theta minus 1. I'll probably use this one because if we go look at our example, sine is a little bit easier to work with than the cosine output, right? This negative 2 root 10 over 7, that's kind of ugly. So let's say this is 1 minus 2 sine squared theta. 1 minus 2 Sine squared theta. You don't have to use that one, though. You could use something else. Maybe you should check that. So we're going to end up with 1 minus 2 times 3/7 squared. So this is 1 minus 2 times 9 over 49. So this is 1 minus 18 over 49. And here comes some arithmetic. 1 is 49 over 49. So 49 minus 18 is 31. So there we go. Cosine of 2 theta is 31 over 49 on this thing. That works out pretty well. So one of the things that we can think about then is, wait a second, why is the sine output negative and the cosine output positive when our angle was in second quadrant here? Shouldn't sine be positive and cosine be negative? Well, that's true for theta. Theta is the angle that's not in quadrant 1, but now we're looking at double of that angle. So you can think you've got this angle in the second quadrant. If you double that, it's not going to be in the second quadrant anymore, right? So this one, we can see where it is. Our sine value is negative. Our cosine value is positive. So this is living right over here in quadrant 4 somewhere. Quadrant 4. We don't know exactly what the angle is. This isn't some known angle that we recognize, but we know where it is because of the signs on these outputs. Cool. So that's how we can use some of those formulas. There are certainly other examples that we can mess around with. So here's a quick question. If you can double an angle, can we halve an angle? This is the verb form of half. Can we find some information about half the angle? So if we're looking at half angles, those are obviously related to double angles. So we're just going to notice that theta is really half of 2 theta. And so when we had all this stuff that had cosine of 2 theta, and it was written in terms of stuff with angles just theta, we'll notice that all of those angles were half of 2 theta. So we're just going to reverse all those things. So for instance, we've got cosine of 2 theta equals 1 minus 2 sine squared theta. If we go ahead and solve this for the sine squared theta, just like this, then suddenly, hey, theta is half of 2 theta. Now that seems obvious, but now we're starting with some angle 2 theta here. We evaluate the cosine of that angle, and then we throw it into this formula, and we get the output for sine squared of that thing. Similarly, if we start with the cosine of 2 theta and we have it written in terms of cosine stuff, so in this one I use the 1 minus 2 sine squared theta, here I'm using the 2 cosine squared theta minus 1, then I can solve this for cosine squared, and it's going to look really similar. We're going to add 1 to both sides, do some work with dividing and all that kind of stuff, and if we solve this, there. Cosine squared theta is 1 plus cosine of 2 theta. And again, theta is half of 2 theta. This seems like a super obvious thing, but this is the angle that we start with. And now we can at least get the squared versions of the outputs of these functions using these 2 formulas right here. These are just directly coming from that double angle on the cosine function. So these formulas, we typically call these power-reducing formulas. If you remember back to the beginning of the video, I said we're going to talk about power-reducing formulas and half-angle formulas. So these are technically the power-reducing formulas. The reason we call them that is because we take some sort of a sine squared and we write it in terms of cosine with no exponent. So we know the exponent is actually 1 on here. So we reduced the exponent on sine. And for this one, for cosine squared, we can reduce the exponent by writing a little exponent of 1 on there. So we call these power-reducing formulas because what you can do is take some sort of a sine squared term and get rid of that exponent of 2 on it by substituting it out for this whole piece. It's a little uglier, it's a little messier, but it does not have that second degree exponent on it. Sometimes that's really helpful. So we call these power-reducing formulas because they reduce the power on the term. If you want the half-angle formulas, we'll just go back to these things and we'll say, all right, we've got some squared stuff, right? So let's just square root both sides. Now, if we do that, we have to look at the positive and the negative versions. So we're going to look at this plus or minus square root. And then we're going to do a little variable substitution. So we really hammer home the fact that these are half angles. So what we're going to do is we're going to say, all right, instead of theta, let's pick some other angle, alpha. And we're going to say, all right, this is alpha over 2, half of alpha. And so now 2 theta ends up being alpha. So just like we said, theta is half of 2 theta. Alpha over 2 is half of alpha. So this is what this looks like. We take that nice little square root on both sides, throw some plus or minus stuff on there because we want both versions of this, and then we've switched out, oh my gosh, did I not do it? This is supposed to be, I'll change this in the notes that go up. That is supposed to be alpha over 2. So sine of alpha over 2 is going to be equal to plus or minus the square root of 1 minus cosine alpha over 2. Oh, okay, I changed it on this slide. Cool. I'll change it on that other one as well. So sine squared equals, the cosine one now, cosine squared theta equals that 1 plus cosine of 2 theta. We can do the plus or minus square root to get rid of the exponent, throw in that alpha over 2. So these are our 2 half-angle formulas. So these half-angle formulas are actually not that big of a deal to get at all. There's really not much work out of them. So typically, these ones will be provided for you, and then you can just kind of rewrite them or do some work or something like that. Sometimes you'll see these formulas with just the alpha over 2 and the alpha, but they won't do the square root stuff yet. So it'll be like sine squared alpha over 2 equals 1 minus cosine of alpha over 2. But the stuff that I've got boxed is the stuff that you'll pretty much find in every trig textbook or every calculus textbook or in some physics textbooks, because these are pretty commonly used formulas. All right, notice one quick thing. The plus or minus here does not mean that there are always 2 right answers, that you can get both the plus and the minus versions. It means that both of those are possibilities, and we have to work out which one makes sense. If you know what alpha is, by knowing what alpha over 2 is, then you know what quadrant you're in. And so, if you know what alpha is, then you know what alpha over 2 is, and so you know what quadrant this is in. So for instance, if alpha over 2 is in the first quadrant, then we know that sine and cosine of alpha over 2 are positive. If we know that we're in the fourth quadrant on this thing, then we know that the sine output is going to be the negative one, but the cosine is going to be the positive one. So just think about what quadrant alpha over 2 is in. When you have that angle, think about what quadrant you end up with, and that's going to tell you the correct sign. So both signs are not correct, the positive and the negative ones, at the same time, but both of them are possible depending on what angle we're thinking about. All right, so jump into this. Find cosine of 67.5 degrees. Find sine of pi over 12. These shouldn't take too long, especially when I give you the little hint that says 67.5 is really equal to, 135 over 2 degrees? So this is half of a known angle, 135. And similarly, pi over 12 is half of pi over 6. So your alphas are 135 and pi over 6. I'll pause the video, I'll let you mess with those things, and then I will start this up with some solutions on here so you can just double check and make sure you're doing okay. So, hopefully this is what we're looking at. Let me just run through the green one first in the top, and then we'll do the blue one on the bottom. So, I went ahead and just plugged in 135 theta over 2 in here, just to really emphasize the fact that that is my 67.5 degrees. So cosine of 67.5 degrees is 1 plus cosine of the double angle, or I guess the one that this is half of, 135 degrees, all over 2. So I've drawn 135 degrees here. 135 degrees is 90 degrees plus 45 degrees, so it's right in this second quadrant. And I know my reference angle is also 45 degrees. So I've got that nice isosceles right triangle. -1, +1, root 2. Here, I know it's -1 on this side length because I'm talking about x values. So I want to find the cosine of that. That's -1 over root 2, or I'll say cosine of 135 degrees is, I probably should have written this in already, but oh well, -root 2 over 2. So I just plugged in -root 2 over 2 here. Then when I subtract this thing, I'm going to say, well, I really want 2 over 2 in for 1, so I can subtract fractions. So that's why I have this 2 minus root 2 over 2. all over 2 under a square root. Very confusing, lots of 2's. But it ends up with 2 minus root 2 over 4, all under a big square root. Then, since 4 is a perfect square, I just took the square root of 4 on the bottom and said, well, there we go. That's just a 2 now. Now the square root's just on the top. I know it's positive because 67.5 degrees is in this first quadrant somewhere over here. And so I know that the x value of the coordinate here is going to be positive. So cosine's output is going to be positive. Cool. For sine of pi over 12, I know that pi over 12 is half of pi over 6. So really, I've got this sine of pi over 6 over 2. That's really just pi over 12. So I do the square root of 1 minus cosine of pi over 6 over 2. Notice I don't use sine here. I use cosine for both of these. I'm just subtracting instead of adding in this case. Cosine of pi over 6 is real easy. It's root 3 over 2. So this is 1 minus root 3 over 2 over 2. And so I've got, again, I'd made my 1 a 2 over 2 just like I did over here. So I've got 2 minus root 3 over 2 over 2. And then the same kind of stuff is happening. But we end up with this. Again, I'm leaving it positive because I know pi over 12 is in the first quadrant somewhere. And so I know that the sine of pi over 12, the y value there on the unit circle, has to be positive. So I could have plus or minuses in front of all these, but it just so happened that both of these angles are in the first quadrant. And so I know that the coordinates, x and y, are both going to be positive. All right, so here's your quick summary. Double angle formulas. This is what we've got. We've got these 3 consistently different ones here for cosine of 2 theta. And you'll be given these. Maybe you'll be able to pick which one to use in which circumstance. Remember, we used this one in our one example, but that was only because the value that we had for sine was a pretty easy one to work with. So you can kind of pick and choose which one you want to work with depending on what information you're given. And then we've got these power reducing or half angle formulas. And really, I think they're the same thing, right? It's just taking the square root of both sides and then rewriting the notation a bit to really emphasize the fact that alpha over 2 is half of alpha, right? We'll be seeing these most, and you can create these other ones from there very easily without really having to think too much about it. Remember the trick with these plus or minuses? The plus or minuses aren't true all the time. We have to figure out what sign is true based on where alpha over 2 is, that half angle. I think that's all we've got for this one. So not a terribly long video. Hopefully that's okay. Jump into some examples. Try and at least recognize these formulas when you see them. You don't have to have them all memorized, but it's really nice eventually, especially for those power reducing or half angle formulas, to know kind of what's going on. One of the things that I've always heard that I think is kind of clever is on this first one, the main thing to remember is sine is minus. Sinus minus. That sounds like a weird thing, but really what we're saying is the sine function is minus, because these are the same formulas, but one of them has a subtraction instead. So sine is minus. Maybe that's helpful to remember. Go ahead, jump into some problems. Let me know if you have any questions on things. Good luck, everybody.